Dear student, in today's lecture we start new article coefficient of emission or emissivity from chapter number 3 kinetic theory of gas and radiation. Now let me learn what exactly mean by emissivity. You can see formula here. So here by formula you come to know what is emissivity. So this is the ratio of R divided by RB. Now R is what? R is emissive power of ordinary surface and Rb is emissive power of black surface, perfectly black surface. And ratio of these two emissive powers is called as coefficient of emission or emissivity. This is the ratio of same quantity, so don't have any unit. For perfectly black body, the value of E is 1. For perfect reflector, the value of emissivity is 0. For ordinary body, the value lying between 0 to 1. For copper, means for metal, you remember it is approximately zero point 0.3. Means for metal, it is near about zero point 0.3. Now, after this coefficient of emission, next article is Kirchhoff's law of radiation. Now, what is the Kirchhoff's law? Mathematically, the Kirchhoff's law can be written like this: A is equal to E. This is the mathematical statement of Kirchhoff's law. At a given temperature, means temperature must be constant. When temperature is constant, then A is equal to E is the Kirchhoff's law. Now A is the coefficient of absorption, E is coefficient of emission, and both are equal at given temperature. And this is the Kirchhoff's law of radiation. Now we have to prove this Kirchhoff's law of radiation. So this is a theoretical proof. We consider here two bodies. The first is a body O, which is the ordinary body, and second one is body B, which is a perfectly black body. They are enclosed in constant temperature enclosure. So this box is constant temperature enclosure. Now we consider that capital A is the area of each body. For body O as well as body B, the area is capital A. Small a is the coefficient of absorption of ordinary body, means body O. E is coefficient of emission of the ordinary body. Capital R, emissive power of the ordinary body. Capital R subscript B, B for black body, that you remember. RB is the emissive power of perfectly black body B, and Q is the quantity of heat incident on each body. As both the bodies, body O and body B, they are in thermal equilibrium. Thermal equilibrium means the temperature is constant. According to the previous theory of heat exchange, if they are maintaining same temperature, it means that quantity of heat absorbed and heat emitted both are same. Okay, heat absorbed and heat emitted both are same. Now this we are writing for body O. So for body O, quantity of radiant heat energy absorbed is equal to quantity of radiant heat energy emitted per unit time per unit area. You know that this emissive power having a formula, this Q upon it. So by this formula we can write quantity of heat emitted is equal to RAT. So this is the formula. But here per unit time means time is 1. Per unit area means area is 1. Time is 1, area is 1, then Q is equal to R. You can see here heat emitted is R. Similar manner, you know that coefficient of absorption is given by this formula. So heat absorbed is given by formula A into Q that you can see here. So A into Q is equal to R. This is equation number 1. This is written for body O. So no, this is written for body O, means ordinary body. Similar manner we can write it same equation for black body also. Similarly for body Quantity of radiant heat energy absorbed per unit time per unit area by body B is equal to quantity of radiant heat energy emitted per unit time per unit area by body B. ठीक है? So we write the formulas here. By same formulas, we can write here Q is equal to RB. Same formula here. Small a is 1 for the black body. So only Q to the left side and right side it's a black body. So RB. Now here we get equation 1, equation 2. So we have to use equation 1 and 2 for the further mathematical process. Now here dividing equation 1 by equation 2 we get. So one side we consider left side AQ divided by Q is equal to right side is R divided by RE. So here Q get cancelled. So we get the next equation A is equal to R divided by R. But R divided by RB is the formula of E, coefficient of emission. So we can write here A is equal to E. And this proves Kirchhoff's law. Hence Kirchhoff's law is proved. I hope you understood the theoretical proof of Kirchhoff's law. Now next article is spectral distribution of black body radiation. Now you can see here the graph of radiant power versus wavelength. Radiant energy emitted per unit area per unit time by a black body depends on its temperature. Hot objects radiate electromagnetic radiation in large range of frequencies. Hence, the rate of emission per unit area is a function of wavelength of emitted radiation. From experimental curve, it is observed that. So this is a black body spectrum. This is the radiant power emitted by black body versus the wavelength graph for different temperature. You can see here 3000, 4000, 5000, 5500. These are the different temperatures. Okay. Now the experimental facts. First experimental fact is at given temperature, the energy is not uniformly distributed in the spectrum. It is a function of wavelength. You can see here for a particular temperature, the radiant power or radiant energy, we can say that it is for this 4000 Kelvin. This is a graph. It is not uniformly distributed. It is a function of wavelength. As wavelength changes, radiant means for particular wavelength, radiant power is different. At a given temperature, again, when a particular temperature is there, radiant power initially increases. You can see here the graph is going initially up, then here the maximum value and then decreases, reaches its maximum and then decreases. The wavelength corresponding to radiation of maximum intensity, lambda max, is a characteristic of temperature. Means here, so when we are considering maximum radiant power or maximum emissive power, so that time this is the wavelength, lambda m we can use. Second time when the temperature is maximum, this is the lambda. Third time, this is the lambda. So it is a function of temperature. And the relation between this maximum means wavelength corresponding to maximum emissive power and the temperature we have to write in one of the law, and that law is called as Wien's displacement law that we learn later. But here this lambda max is characteristic of temperature. This is the observation. The next one is area under the curve. Means the area under this curve represent total energy emitted per unit time per unit area by black body at all wavelengths. Next is peak of the curves shift toward the left, shorter wavelength. That is, value of lambda max decreases with temperature. You can see here. So this is 3000 Kelvin. This is a lambda wavelength. When it is 4000, this is a wavelength corresponding to the maximum emissive power. Then when it is 5500, this is a wavelength corresponding to the maximum this emissive power or maximum radiant power. So it shifts towards the left, means it decreases. So it decreases with increase in the temperature. So generally we can write the relation here between these two, inverse relation, and this is a Wien's displacement law. Next one is at higher temperature, the radiant power or total energy emitted per unit time per unit area corresponding to all the wavelength increases. Next one, at a temperature 300 Kelvin, around room temperature, means it is 27, 300 minus 273, that is around 27 degrees Celsius, means at room temperature. The most intensity of these waves has wavelength of about 5 into 10 raised to minus 6 meter. The radiant power is smaller for the wavelength different from this value. Practically, all the radiant energy at this temperature is carried by waves longer than those corresponding to red light. These are infrared radiation. Next one is Wien's displacement law. Just we already discussed it. So it is lambda max proportional, inversely proportional to absolute temperature. So lambda max is a wavelength corresponding to maximum radiant power or emissive power is inversely proportional to the absolute temperature. The wavelength for which emissive power is maximum is inversely proportional to absolute temperature. Symbolically, we can write like this. Now we write the constant of proportionality B. So B is called as Wien's constant. So we can write lambda max into T is equal to Wien's constant, whose value is 2.897 into 10 raised to minus 3 meters Kelvin. This law is useful to determine temperature of distant stars, such as moon, sun, etc. Now next law is Stephens-Boltzmann law of radiation. In short, Stephens law of radiation. Let me learn the statement. You can see here the mathematically the law is given by formula R proportional to T raised to 4. Now here, in word we can write rate of emission of radiant energy per unit area or power radiated per unit area of perfectly black is directly proportional to fourth power of its absolute temperature. Same formula you can write like this well. So Q upon AT proportional to T raised to. The quantity of radiant energy emitted is Q per unit area per unit time is directly proportional to fourth power of absolute temperature. In that way also we can write. Now here we introduce the proportionality constant sigma. It is called as Stephens constant, whose value is 5.67 into 10 raised to minus 8 joule per meter square per second per Kelvin raised to 4. Dimension by of this Stephens constant we get L0 M1 T minus 3 K raised to minus 4. The power radiated by perfectly black body depends only on its temperature and not on any other characteristics such as color, material, nature of surface. So here this law is written for the black body. So when you are writing the statement here, the black body word is very important. So here you can see perfectly black body, this word, because this law is written for black body. Now let me consider if Q is the uh, amount of radiant energy emitted in time t by a perfectly black body of surface area at temperature T, then we can write Q upon AT is equal to sigma T raised to 4. For ordinary body, we can write Q upon AT is equal to E sigma T raised to 4. So when we are writing this, simply we can write here R is equal to sigma T raised to 4. Multiplying both sides by E into R is equal to E sigma T raised to 4. Then this E into R is RB. It is equal to E sigma T raised to 4. And this is the Stefan's law for ordinary body. Okay? I hope you know how we get this by using a formula of coefficient of emission. We can write E into R is equal to RB. Now E is emissivity of surfaces. Now if we consider that perfectly black body whose temperature is capital T is kept in a surrounding which is at lower absolute temperature T0, then the energy radiated per unit area per unit time is energy. Okay, this is the energy absorbed from surrounding. Therefore, net loss of energy, and so here it is sigma T raised to. Okay, it is sigma T raised to 4 is the energy radiated per unit time by body, and this is the energy absorbed. So the net loss of energy by perfectly black body per unit time per unit area is given by this form. Difference between these two values. So here we can take sigma common, so we get T raised to 4 minus T0 raised to. For ordinary body, same formula we can write by multiplying E to the right side. You can see here multiplied by E. Similar manner, we are written here the formula by multiplying to by E. Now, here the chapter is over. Now let's see the MCQ question from the exercise. In an ideal gas, molecule possess. So option one is only kinetic energy, both kinetic energy and potential energy, only potential energy, neither kinetic energy nor potential. And the answer is only kinetic. This molecule doesn't have potential energy, so only kinetic. And this kinetic energy is a function of temperature. Next MCQ. It is MCQ number 2 from exercise. Mean free path lambda of molecule is given by. You can see here the four options. In these four options, you have to find out the mean free path formula. And you note here mean free path is given by the option C. So option C is the right answer. Now next question. If pressure of ideal gas is decreased by 10% isothermally, then its volume will listen. You know that gas equation PV is equal to RT. Isothermally means temperature is constant. So temperature is constant. Okay? And then pressure is decreased. R is already constant. So we can write here PV is equal to constant. This is the formula. So P inversely proportional to volume. So here pressure decreased. So volume increased. So volume is increased in the two options. So option B and option D. So these two options are deleted. So out of these B or D, one option is the right option. And if you do the calculation here, this is the right answer. Now next is MCQ number 4. If A is 0.72, R is 0.24, then value of T is, you know that A plus R plus T is 1. Substitute A and R, then you get the value of T. After doing the calculation, we get this answer. So A is 0.72 plus 0.24 plus T is equal to 1. So the addition of these two is 0.96. So T is equal to 1 minus 0.96. It is 0.04. Next question is ratio of emissive power of perfectly black body at 1327 degrees Celsius and 527 degrees Celsius is ratio of emissive power. So emissive power is proportional to T raised to 4 for the perfectly black body. So R1 by R2 is equal to T1 by T2 raised to 4. So T1 is this 1327 plus 273 Kelvin and 527 plus 273 raised to 4. This we have to solve. After solving this, we get the answer is 16 as to 1. So this is the answer. Now we stop here. The remaining problem we see in next session.